Good afternoon, everyone, and welcome to the CSS seminar series of the Center for Computational Social Sciences at Koç University. I'm Mirhangan. I'll be moderating this session, and I'm very pleased to open today's session. That is the first seminar of the spring 2026 semester. And thank you all for joining us online. Again, it's my great pleasure to introduce our speaker today, Dr. Yian. Dr. Yin is an information scientist and computational social scientist whose research develops and applies innovative computational methods to understand how scientific progress and innovation emerge. His work examines how individual, social, and environmental forces jointly shape scientific discovery and creative production. Beyond science itself, he uses innovation as a lens to study broader social processes, including culture, cultural, artistic production, media dynamics, public policy, market competition, and even conflict. Dr. Yin's research has appeared in leading journals such as Science, Nature Human Behavior, and his work has been featured in major public outlets including Forbes, Scientific American, The Atlantic, Harvard Business Review, and MIT Technology Review. In recognition of his contributions, he was named to the Forbes 30 Under 30 list in science back in 2023. He received his PhD in industrial engineering and management science from Northwestern University, where he was affiliated with the Northwestern Institute on Complex Systems and the Kellogg Center for Science and Innovation. He also holds a bachelor's degree in statistics and economics from Peking University. So he will be today presenting his talk titled Scientific Production in the Era of Large Language Models, Early Evidence from 1 Million Preprints. Yeah, thank you so much for joining us today. The floor is yours.
Thank you. Thank you. Good afternoon, everyone. Thanks for coming, bearing with me late. I know it's already 5 p.m. um, there. And thank you for the very comprehensive intro. I guess I can go a bit faster with the first few slides. So, hi, everyone. My name is Yian. I am, computational social scientist by training. Great pleasure to be here sharing some of our, latest work around thinking about the interrelationships between large language models and scientific production. So let me start by saying, I am a science of science person. So for those of you who are not familiar with this field, this is a kind of emerging field where we try to think about scientific approaches to understand science and innovation itself, which is the fundamental engine that fuels economic growth and human prosperity. So we think about questions such as how science itself evolves over time as a complex ecosystem, or taking further back, how does it interact with the broader society, and so on and so forth. Methodologically speaking, this research agenda is only possible through a combination of interdisciplinary toolsets. First is many decades of social science literature about science and innovation, developed in areas as diverse as history, sociology, psychology, economics, information science of science and innovation, and so on and so forth. In parallel to this conceptual literature is mathematical modeling tools developed in complex sciences. So here, the idea is to build general stochastic models that can mimic the behavior and decision-making processes of scientists and innovations, such that we can construct formal modeling grounds of success and innovation in scientific domains. These theoretical frameworks are most powerful when combined with the recent opportunity of large-scale datasets that captures different aspects of science and innovation with the unprecedented scales and details. So here I'm only showing you a few datasets that we have been exploring in our own research, which, as you can see, what's most exciting here is not just a number, hundreds of millions of scientific papers, but the key is indeed our capability to link these papers to other important scientific and social institutions. And by applying a range of data science and artificial intelligence tools on these large-scale datasets, we are now able to map out the complex relationship and interactions both within and beyond science, which not only help us to understand the evolution and broad impact of new scientific knowledge, but also contributes to the broader computational social science literature by offering new analytical as well as empirical frameworks. So let me spend a few more seconds on this picture that I have already shown you. So this is taken from a review paper on Science of Science, published on Science a couple of years ago. So I actually like this illustration, although I'm not one of those who made it. So very much illustrates the idea. You can see in Science of Science, we study how different ideas, teams, individuals, or papers interacting with each other at a very large scale across decades or even centuries, right? So one day I was looking at this picture and I realized, although it's a very beautiful visualization, we are missing some of the key elements that is important nowadays in science, which is all these AI tools, Cloud, ChatGPT, Grok, Gemini, DeepSeek, and so on and so forth. Okay, so these are kind of tools that we increasingly rely on across different parts of scientific production. And now the natural question for not only as a scientist, but especially someone who does science of science research is how should we think about the role or the function of these large language model tools on our daily scientific production? Indeed, this is nothing new, right? So this is the kind of questions that we keep talking about with our colleagues, with our students during the past 3 years or so. And here I'm showing you some of the, I would say, maybe slightly outdated data. This is survey, which I believe Nature did like 1 or 2 years ago. Basically, it's just, mass email scientists asking them about their uses of AI and their concerns about AI, right? And you can see there's a very diverse set of potential benefits as well as challenges. People have been using it to do writing, to refine their writing, to see whether they can improve the efficiency of data collection, processing, peer reviewing, populating citations, and so on and so forth. At the same time, there have been emerging concerns across different aspects. What about ethics? What about lack of transparency? How do we train our students to be ready for the new AI wave, right? And so on and so forth. So these are extremely important data points. But from a science of science aspect, I see that as a starting point, not the eventual answer to this question. Because we can think about a lot of different ways people are incorporating these tools into their daily scientific production. But from macro aspect, what are the systematic ways for us to quantify some of the macro impact of LM on science? So in other words, rather than just speculating on narratives about potential impacts on science, potential impacts of LM on science, we want to understand what's actually happening at scale in the field across the scientific enterprise. How exactly are researchers using these tools? What are the measurable effects on productivity, quality, knowledge discovery, and so on and so forth? So that's kind of a key question that I asked my student to start looking at roughly 2 years ago. And they looked into this very carefully for a week and come back to me telling me a very clear answer, which is this is something that is almost impossible. Okay. And here's why. There are indeed a few technical challenges when we try to quantify the macro impact of LM on science. First is to think about adoption. Okay, when do people start using AI? This is indeed something by itself that is very hard to be quantified. Why is that? AI adoption is highly dynamic. Think about technological landscape 3 months ago versus nowadays. It will be very different, right? And the global adoption remains in its infancy and keeps increasing. And this fact is further complicated by the additional lag in publication cycle. A paper that was written, let's say, nowadays, assisted by AI, may need to wait for months, if not years, to be published and enter the traditional publication datasets. In parallel to this is a well-known technical challenges in pinpointing when, where, and how AI has been adopted in scientific research. Some of the journals have released their own policy regarding how you report your AI uses. But recent studies have shown that these kind of policies haven't been very successful. Indeed, many of us are not completely reporting how exactly have we been using AI. And the last point, which very much relates to a key capability feature of large language models, this is a general purpose technology. What this means is that LLMs can be used through a few very different channels. In other words, the benefits as well as risks of AI could also be distributed across very different channels, not just within one channel. This further increases the challenge for us to understand the impact of LLM on science in a systematic way. Okay. So we've tried to look into some data and figure out some of these technical issues. I will say we are not quite there having the entire picture yet, but very excited to share some of the initial progress through this line of research. So today I want to focus on one of the studies that we just got published last December on Science. So it's titled Scientific Production in the Era of Large Language Models. So what we did in this paper, the motivation here is very simple. We want to put together a bunch of data sets, large-scale data sets, so that we can robustly analyze some of the impacts of LLM on science. And our primary focus here was on preprints. We focus on preprints partly because these are the kind of publication formats that should be associated with shorter time delays so that we can really trace the latest of scientific production. We look at three different leading repositories. We look at arXiv, 1.2 million papers spanning physical sciences, mathematics, computer science, and so on and so forth. To make sure our findings are not just skewed by the predominance of recent AI research itself, we specifically excluded AI research itself from our analysis. We also look into other fields. For example, in life sciences, we look at the bioRxiv. So this is one of the leading repository for life sciences. And we look at the SLRN, the Social Science Research Network, which many of you in the room have been already very familiar with. This is a leading preprint server for social sciences. Okay. And to enhance these data sets, we not only just look into the paper level metadata, but we also connected them to other sources such as Semantic Scholar and OpenAlex so that we can populate additional citation metadata. This allows us to enrich our data by extracting references cited by each preprint, tracing the eventual publication outcome of these papers, as well as performing high accuracy author name disambiguation. Okay. And we will be talking about how exactly we are using these data sets in a bit. But before that, the key to this analysis is our growing capability to estimate the uses of large language models in scientific writing. So we are building on one of the most commonly used approach that was just developed 2 years ago. So this is a word frequency-based approach to estimate to what extent people have been using large language models in their scientific writing. So the idea here is very simple. We train a model on both human written and AI generated corpora. Basically, you are taking papers published before 2023, which had to be wholly human written, and you also ask AI to rewrite these papers, which you get a comparable but purely machine generated corpora. And we estimate their underlying word or phrase distributions, which allows us to compute a maximum likelihood score, which we call alpha, that reflects the extent to which a paper was likely modified by a large language model. So for each paper in our dataset, we calculate its alpha, which is a fraction of LM uses in scientific writing. Now, given this metric, we can answer a bunch of questions that relates to the real-world impact of LM on science. So questions could be as simple as the very first-order effects, like how do large language models change the rate at which we publish scientific papers? And I'm going to answer this question based on a very straightforward metric of productivity, which is simply how many papers are posted every month. In particular, to answer this question, What we did here is to construct a panel dataset that tracks the monthly productivity of over 160,000 active researchers between 2022 and 2024. For each paper written by these authors since 2023, we apply this text-based AI detection tool, which I just talked about. This allows us to identify whether an author has adopted LLMs in their scientific writing, and in that case, when their first adoption occurred. So what this essentially tells us is that now we can separate the authors into two groups, the adopter group as well as the non-adopter group. To estimate the impact of LLM adoption on your future scientific production, we use a stacked diff-in-diff regression, which is a method that's frequently used by economists. So the idea is very simple. We are going to see whether the productivity dynamics of the adopters and non-adopters are similar before adoption happens. And then we are going to estimate the relative changes in number of papers published every month after adoption happens for the adopter group. Again, relative to the non-adopter group that are otherwise very similar to them. Another technical point I want to highlight here is that instead of a linear regression, we use a Poisson regression. This is partly because most of us don't publish a huge number of papers every month, right? So that's a very sparse and discrete data. So if you haven't published anything last month, don't worry about that. We take care of that sparsity in our data very seriously. Before I show you the results, a few disclaimers, okay? This is very important. This is not a causal estimate. We are using diff-in-diff, but we understand there could be self-selection in technological adoption. This is something that is hard to escape from given the current landscape of AI adoption, but hopefully after proper controls, we feel some of the estimates will still be useful. And also, the detection of LM usage could be noisy. I'm sure we are seeing something that tells us some information, but that's not going to be perfect. And also, a lot of papers have been written by a team instead of a single author. So sometimes it could be hard for us to pinpoint who exactly on the team writes this specific paper, right? And there are also well-known challenges in author name disambiguation. And we did our analysis between 2023 and mid-2024. So we are essentially looking at a snapshot of a rapidly changing landscape. So I see this as limitations as well as promising directions for future research. But before that, let's take a look at what we really see in the data. This is what we see from the archive data. X-axis plots the relative time, where 0, the gray bar here, represents the months where people started using LMs at the individual author level. We are seeing a very clear pattern here. Before this usage, we are seeing the adopter group and the non-adopter group are following very similar trends in the number of papers they posted every month. But immediately after the first adoption of LLMs, we are seeing a pretty big jump here, representing those who use LLMs are associated with a higher productivity after their first LLM uses, at a scale of roughly 30% in archive data. And next question we ask, is this something that's just a particular about archive? Which turns out to be not the case. We do the exactly same thing on bioRxiv and SSRN. And what we are seeing here is very consistent patterns, although the results are a bit noisier because we have smaller sample size. Regardless, on bioRxiv and SSRN, we see researchers who adopted LMs produced actually an even higher fraction, as a magnitude of 50% more papers per month following their first uses of these tools in scientific writing. When we first saw these results, my first reaction is that there must be something wrong. It couldn't be something that huge. So that's why we did a bunch of robustness checks, including some of the limitations we talked about. We not only match these authors based on their previous scientific field, we also look at their prior productivity. We want to compare apples to apples. There could be noises in how we determine whether a paper is written by LLM. So we vary different thresholds for LM detection and cross-validate our approaches with independently developed alternative AI detectors. We also thought about the problem of big teams where not everyone contributing equally to the writing stage. So we restricted in our robustness checks, we restricted our analysis to only first and last author papers. We also explored heterogeneity across scientific fields, team sizes, career stages, and so on and so forth. So what we are seeing in our data is that sometimes the specific estimate of the coefficients may vary, but across all different specifications we are looking at, we see a widely consistent pattern where there is always a very strong association between first uses of large language models and increase in scientific productivity. Okay, so this is the first set of our results. If you look at the quantity of scientific production, then we are basically looking at a huge increase in quantity. So this raises the question of why we are seeing such a big increase. A productivity jump we just observed may stem from the use of generative AI across multiple research tasks. This could include, for example, idea generation, literature review, coding, data collection, analysis, and so on and so forth. But for the analysis that we were looking at, which is until May 2024, I would argue LLMs likely has the largest impact not in these other tasks, but in writing itself. And because if you think about the daily scientific production practice to create distinctive scientific works, we must present compelling written arguments, link manuscripts, arguments, methods, and results to prior literature. We need to detail and contextualize the most important findings and articulate what can be learned from our finding, right? So these complex writing tasks are very time consuming, especially for people who are communicating in a non-native language. So in other words, one way to validate this hypothesis that is writing makes a major difference is to look at the heterogeneity between native and non-native English speakers, which is something that we can't pinpoint 100% correctly, but we can largely approximate using either race and ethnicity infer from author names, or we can also infer some related information from the geography of research institutions. And here's what I'm going to do here. I'm going to first look at the inferred race and ethnicity from author names and breaking down researchers to different subsets, estimating the magnitude of productivity boost post-adoption for each of the subgroups. Okay. For example, on arXiv, we know overall there's roughly 30% productivity increase. But we can now estimate this for different subgroups, right? So overall, we are seeing there appears to be productivity increase associated with each different group. But Asian scholars, especially those with the East Asian name, are more likely to be associated with a larger productivity increase, while white names, especially English names, are more likely to be associated with a still positive but slightly lower increase in their productivity after their first uses of LLM. And again, we repeat this across all three datasets. We are seeing huge heterogeneity depending on field and also characteristics. The estimated LLM boosts productivity can be as low as 10% for native speakers working on physical sciences, or it could be as high as something larger than 80% for social science scholars in China, Korea, or Japan. So what this means? I think about this in two different ways. On the one hand side, we are seeing robust and practical meaningful gains across all groups. So this means we are seeing something that's not just useful for one subgroup, but applies to different subgroups. But at the same time, we are seeing huge heterogeneity, which means these results are consistent with the emerging view that AI in many cases can equalize skills across individual ability levels. In this case, AI is radically reducing the cost of writing as a second language. And the productive effects we estimate here appear substantial enough to imply a significant shift, not just at the individual level, but in the global market share of scientific production, which favors scholars in non-native English-speaking geographies. So this is the first set of results I want to share with you. And I was seeing a comment in the chat, so why don't we, talk about that bit.
Sorry, I'm just going to read it out loud.
Yeah, sounds
Erdem,
good.
you're saying you have clearly established the impact on LLM adoption on scientific productivity in a quantitative sense. Do you have plans to analyze qualitative improvements? This could be operationalized in a follow-up study as number of citations or whether a paper is later published in a peer-reviewed journal. We're going to have a
Um,
standalone Q&A session. I mean, we can also get back to this question if you want later, but I mean, it's up to you really if you'd like to answer now.
yeah. So I would say, like happy to take clarification question, throughout, and we can leave more discussion, more substantial discussion towards the end. But for this specific one, great question. You are predicting what I'm going to tell you next. Okay. I promise I will get back to this exact question in 5 slides.
Thank you.
Okay. Any other clarification questions before we proceed?
I don't see any other questions in the chat box at the moment. I think we can
Okay.
continue.
Okay. Great. Oh, I see another one. Okay.
Okay, now there is one. Since LLM writing style changes over time, how robust is alpha to changes in the AI reference corpus?
Yes, that's a great question. So I think about this in two different ways, right? One is that, yeah, right, it changes. And there's always a moving target issue, not just about technology changes. Once I know something, we are really, tell our people this is LM written, very likely I'm going to remove that word in my final submission, right? So what we did in our analysis is we actually tried different prompt techniques, different versions of the model, different models. We also look into Llama, we look into earlier and newer versions of ChatGPT. The results appear, remarkably consistent. But I'm totally with you that this is something that's very hard to be done perfectly. And to be honest, if we are doing this analysis again nowadays using 2025 data or even 2026 data, it's a bit unclear to me to what extent we will be seeing this remarkable consistency because nowadays there have been an even wider set of tools people been using. People are now used with all kinds of prompting techniques. And the ironic thing is that if you look at all these commercial companies doing AI detectors, many of them are also doing AI writing humanizer. So it helps you escape from the specific, easily detected parts, right? So my overall response to this is that this is a valid question. I myself is not super concerned with this happening to our data set because we were examining an early period of LM uses, by which time authors don't have a very clear sense of how to escape from AI detections. And we have tried our best to look at how robust this analysis is, not by trying to develop a perfect algorithm, right? But we are seeing here is what we did here is to trying to demonstrate this appear to be pattern that is consistent across different AI detection algorithms we can try. And if this is making mistakes, which I'm sure it happens, very likely it's misclassifying some of the adopters into the non-adopter group or vice versa. So likely what we are seeing here is going to be a conservative estimation, is going to be the lower bound between the productivity of adopter and non-adopter groups after the first adoption happens.
Thank you very much.
Sounds good.
Yeah,
So how about we proceed? Okay.
yeah, let's go back.
So okay, now let me get back to my promise. So far we have been looking into a lot into quantities, right? And the next question is indeed about quality. Okay, here's the way I think about it. I feel like LMs is remarkably good at writing. In many cases, it's not just writing things in a faster way, it's also writing better, beautiful language. But this have implications for the evaluation of scientific quality. And let me make it concrete. So in many cases, when we are reviewing papers, more or less, implicitly or explicitly, some of us may have been judging the book by its cover, where we take writing style as something that's related to scientific quality. For example, if I'm reading a paper that appears to be remarkably well written, this is maybe something that has been written very seriously. Or at the same time, if I am reviewing a paper that's full of typos, grammar mistakes, and so on and so forth, maybe it still has significant scientific value, but that's something that's harder to pass peer review, right? So what this means is that there used to be a common belief that the writing style of a paper may be associated with scientific quality. And this is indeed something that we can measure using science of science matrix. We can look at, for example, writing quality. We use a metric where we call the writing complexity. This is essentially just the negative of flash reading e-score. For those of you who are not familiar with this metric, the intuition here is very straightforward. If we see a lot of long sentences and complex vocabulary in your paper, this corresponds to higher writing complexity, indicating you may be writing English in a way that's not about daily conversation, but very professional writing. At the same time, the real scientific quality is something that's very hard to be perfectly measured, but we follow existing literature where we look at the peer review outcomes. That is, because we were primarily focusing on preprints, we can trace their publication outcomes, looking at the probability of these preprints to show up in a peer-reviewed publication venue, such as a conference or a journal. Okay, so if we see a subset of papers associated with a higher probability of passing peer review, this might be a signal that they are on average associated with higher quality. So first, what if we focus on papers that are really human written, papers where we did not detect the uses of LMs in their writing? For these papers, overall, we are seeing the writing complexity score follows a Gaussian distribution on the top row here across all three datasets. But more importantly, we are seeing something that's confirmed with the hypothesis I just talked about. We are seeing a positive correlation between your writing complexity score, how beautifully the paper is written on the x-axis, and the peer review outcomes, the probability of this paper showing up in a peer-reviewed conference or journal. So what this means is that papers with more complex writing were more likely to be published with a fixed time frame, or in other words, receive higher peer review scores. So this is a pattern for human authored papers, which we are showing in green or blue curves here. But now the question is, what happens when we look at papers written not just by humans, but assisted by large language models? On the one hand side, if you look at the red curve on top, we see for LM-assisted papers, the distribution of writing complexity shifts towards the right-hand side, indicating an overall increase in complexity, which seems to be something good, right? We are now writing more beautiful papers with LMs, greater complexity, suggesting improved writing sophistication. But what's really concerning here is what you see in the bottom row. Okay, when we examine the relationship between writing complexity and peer-reviewed outcomes, we see a striking decoupling between your writing quality on the x-axis and your real scientific quality on the y-axis. For the red curve, which is LM-assisted papers, we see a negative correlation between writing complexity and publication success. In other words, while writing complexity increases, the quality or the perceived value of scientific manuscripts does not improve correspondingly. There are myriad factors that might influence the publication outcome of preprints. How do we overcome this? One thing we can do is to do a robustness check within a specific scientific field and preprint time by adding fixed effects in a regression form. But the alternative way of doing this is why don't we look into something that's more concentrated, not about different subfields, but something specific. So we did another validation task using our peer review data from a leading machine learning conference, which is iClear. So for those of you who have been submitting to the open review, you may be familiar with iClear. So this is one of the biggest international conference on machine learning, ICLR. The interesting thing about this conference is that they open sourced all their peer review reports, not only for those who were accepted, but also for those who went through peer review but were eventually rejected. So we have the entire set, which is 28K free reports for all 7,000 submissions, regardless of final acceptance status. And for each of the paper and the peer review report, we get the peer review score given by experts, which can serve as an alternative measure of scientific merit. So here again, we are using a different outcome, not just a probability of being showing up on a peer-reviewed conference, but specifically for this conference, we are looking at the reviewer score given. Again, we are seeing a very robust decoupling between writing complexity and peer review outcomes. The green curves representing purely human written text telling you before LLM, beautifully written papers are associated with a higher likelihood of being published. But if you look at LM-assisted papers, the red curves, we are seeing a negative relationship between writing complexity and publication success. Okay, we also look into alternative measures of writing complexity, lexical complexity, syntactic complexity, promotional language, and so on and so forth. But again, we are seeing very robust patterns where there's positive correlation between writing and scientific quality for those who are writing papers on them by themselves, but a negative relationship for LM-assisted papers. So beyond the robustness, what exactly does this result mean? I would say this contrast, this decoupling, highlights a very important issue if we think about the widespread uses of LLM in our current scientific practice. LLMs can already enhance the appearance of sophistication in scientific writing. But until very recently, LLMs are not necessarily ready to improve the real scientific substance of the research. And if you combine these two factors together, this suggests that we may be witnessing an influx of AI-assisted papers that appear remarkably well written, but essentially lack substantive scientific quality. And this decoupling between writing style and research quality could challenge existing practices in scientific evaluation and publication. It underscores a need to rethink how we assess scientific work in an era of increasing AI adoption, not just for scientific researchers, but also for journals, funding agencies, as well as research institutions. So a quick recap on this. Over this study, we looked at the large-scale evidence on the impact of LM uses on scientific production. Basically, the approach here is to build large-scale preprint data combined with AI detectors and a diff-in-diff framework. What we are seeing here is the interesting as a contrast between quantity and quality. On the one hand side, we are seeing LLMs boosting scientific productivity, especially for those who are not native English speakers. But at the same time, we are seeing a more concerning picture on the quality side, where we are seeing a decoupling between writing style and research quality in LM-assisted papers. And these results have important implications for the institutions of science. Assuming further advances in AI capabilities, the evidence of an already large AI-driven increase in scientific quality, scientific output, which also indicates there could be shifts in market share of scientific production across ethnicities and nations. But at the same time, it has implications for how our journal should operate, given the massive submissions, many of which appear very well written, not necessarily good in a scientific sense. It also has implications for the new standards and benchmarks to evaluate not individual works, but academic careers across fields. Should we still thinking about the number of papers or other metrics as a valid measure when it comes to funding, awards, tenure, promotion, and so on and so forth? So that's the first study I want to talk about. This is a paper that was published on Science last December. So if you are interested in more technical details, feel free to check out supplementary materials for methods and more robust checks. I realize that we also have 20 minutes left, so I want to talk about something very quickly. This is another study that's related, but still ongoing work. But we are very excited about some of the initial data points we are seeing here. So the idea here is we are seeing increases in quantity as well as a concerning picture in quality, which sometimes mean people are not really using LMs in the most appropriate way. So now the question is, can we go beyond this data analysis and let's do something real? Let's do some real experiment to help people achieve better human AI collaboration in science at scale. Okay, so the idea here is very simple. If you look at the defining mode of modern sciences, it's having collaboration and teamwork. Very few papers nowadays, especially in natural sciences, are written just by a solo author, but it's about collaborations, it's about teamwork. And at the heart of scientific collaboration, it's not just about divide and conquer across team members. It's not just about more people doing more things or more resources given, right? It's also about collaborative feedback. Once I have something worked out, my collaborators will give me sometimes very critical feedback, but that's exactly how I get to improve my initial idea, my experiment design, or even my eventual paper. So from sociology of science and language, science often advances by bouncing ideas off each other. So this is something that, in my opinion, is super important if we really want to understand how good papers, impactful papers are produced. But at the same time, this is something that we have very limited quantitative understanding. Why is this? Collaborative feedback has been time consuming and resource intensive. You really need someone who is deeply knowledgeable about your field so that you can get the most useful feedback. In many cases, there are not so many people around you that can give you that level of feedback. So this is something that takes time. This is also something that requires resources. And one implication of the resource-intensive nature of collaborative feedback is that it could be deeply unequal. People in, for example, US and some of the European institutions may have access to more useful feedback through seminars, through collaborations, as well as other conferences. But at the same time, people in developing countries may have limited access to collaborative feedback, right? And from a science of science aspect, this is something we really want to study, but also really hard to study because collaborative feedback is something that is often largely invisible in data. There is not data on off the shelf that allows you to trace who is giving feedback to who on which specific paper. So we are like, if there's no data, why don't we create some data points? Okay. So what we did here is to run a randomized experiment on scientific feedback at scale. And the key capability we have that allows us to do this at scale is indeed large language models. We now no longer need to hire all these experts to give scientific feedback, but we can develop very good LM-based pipelines to give scientific feedback. So this is a randomized experiment that we did last year, and we are still wrapping up the data analysis across 34,000 manuscripts, hundreds of scientific fields across 135 countries or regions. So let me quickly go through how exactly we achieved this. We started from data collection, which is again preprint data. Okay, we look at the archive, we get all the recent preprints that were recently uploaded to archive. And given this data, we basically did two computational things. On the one hand side, we used bibliometric tools to extract the metadata information, including title, abstract of the paper, including the author information, their names, institutions, email address, and so on and so forth. At the same time, we also developed an LM-based feedback pipeline. Okay, so here the idea is that every time you can just feed in a raw PDF file of the paper, and our pipeline will parse different sections of this paper. And we use a multi-agent tool with in-context learning to provide feedback based on different aspects, the reviews, the title suggestion, grammar check, and so on and so forth. So think about this, not that good, but still useful mini version of the peer review report that you will get if you submit to some of the conferences or journals. And finally, we build on the review generated in step C. We build a customized web page for each paper where we list different aspects that the LMs have found useful for authors to refine their papers. Each of the web page has a specific link that has been hashed. So this is not something that is publicly observable. You only get to click into it if you get the URL to the feedback for your specific paper. And now comes to the key of our design. We generate the feedback for every paper in our dataset, but we did not distribute the information to 100% of our population. Instead, we randomly selected 50% of the papers in our data set as a treated group, and the next 50% as a control group. We did nothing to the control group, but for everyone in the treated group, we simply send out them an email. The email is something very simple. Hey, congrats on your recent archive paper. This is a great work. But there are some feedback, some suggestions that you might want to think about if you are going to refine this paper. Okay, that's the only thing we did to the treated group. No emails to the control group. And we just sit there, wait for a few months to see what happens to the treated group as well as to the control group. So basically, this allows us to offer causal evidence based on this large-scale randomized experiment across more than 30,000 scientific papers. And for the sake of time, I'm just going to quickly tell you two results that we find especially interesting. First is the short-term behavior. On archive and well as other preprint servers, you can not only just post the initial version of your preprint, but after that, you can also post an updated version of your preprint. So we looked at the revision rate. What's the likelihood that within a month, the authors will post another revision of the same paper? What we are seeing here is that compared to the control group, the treated group, those who got the LM-generated feedback, are more likely to post a revision of their original paper. And this is something that's not really happening to the English-speaking researchers, maybe because they don't feel the tool is useful enough. But instead, this is something that is super significant if you look at non-English speaker groups. We also got some qualitative feedback from some of the users telling us they find this tool is extremely useful, and maybe not surprisingly, the vast majority of the positive feedback come from people who are non-native speakers. So this is short-term behavior. Getting this LM-based feedback actually allows people to do more frequent revisions of their original paper. But what's even more intriguing is that we are seeing some long-run practices. If we look at the papers that the authors published after the experiment, their future scientific writing, we also see a difference here. We can apply the alpha estimation that I talked about in the first project and scan through all their future papers. What we are seeing here is that for adopters, I would say this is for those who receive the email nudge, people are more likely to use large language models in their future scientific writing. And again, this is the kind of effect that is strongest among non-English speaking teams. So in other words, we are not just seeing a short-term impact where people are more likely to revise their original paper, but we are also seeing a long-run practice about the long-term adoption of AIs. If you haven't really used the AI before our experiment, after getting initial exposure to LM generate feedback, some of the people find this is something especially useful, such that they also started using LM themselves when they develop their future projects, which have implications if you think about the adoption as well as the long-term impact of AI, not just on individual researchers, but on the global equity and production of scientific research. So I'm going to just stop here. There are two projects, LM and scientific production, as well as LM and collaborative feedback. This is only possible thanks to a lot of my students, collaborators, as well as generous funding support from NSF, Chemie Sciences, and the UK Research and Innovation. I'm all happy to open the floor for more questions, and thank you for your attention.
Thank you so much for this really thought-provoking, fantastic presentation. We do have some questions in the chat box. I'll just read them out loud. So if we ever publish this on YouTube, it will be easier there is also a question from Erdem Yörük, but let's start with that. So Erdem Hocam, you can unmute yourself and ask, and then I'll read the questions in the chat box.
Okay, thank you very much. And this was excellent. Thank you so much. Really so impressive. So I have one question. Maybe please correct me if I'm wrong. I don't know if I have understood correctly, but you have measured so you have observed that those who are receiving this feedback are more likely to revise their preprints after a month.
Yes.
And
Yes.
did you so did you and that feedback was an LLM generated
Mm-hmm.
feedback. And
Yes, yes.
yeah, and I was wondering if that effect of increase in revisions is a result of receiving a feedback per se, or if receiving a feedback, an LLM-based feedback itself. So are we able to differentiate between the two?
Thank you. Thank you. This is a really great question. So I think what you are saying, so basically you can think about different mechanisms, right? One on the one hand side is that it's really, the LM feedback is useful. So people are using some of the points from that to refine their paper. The other thing could be, it's just a feedback or it's just a refinement, right? So it's attention, right? You got someone saying your paper is great, so you got to refine it. I would say we look into some of the content of their changes as well as we are seeing, the differences across different subpopulations. So my interpretation of this is that there could be part of the effects that we can't fully rule out. That's just about feedback, not about LM generated feedback. That's something that we can't fully rule out here. But our whole point here is not just to, compare LM generated feedback versus human generated feedback, which is something we wanted to do, but it's going to be something very costly. What we are trying to do here is that overall thinking about scientific feedback, which is something useful, but has been very hard to be scaled up, especially exactly because of the cost of doing human-based feedback. So I see this more as a test ground saying how can we scale up feedback and then see the overall effects. Whether it is about something like human generated or LM generated is something that we can test in future research because this also relates to both the real quality of this feedback as well as perception, right? It could be LM generated feedback are indeed more or less useful than humans, but it could also be the fact that even given the same set of feedback, if we tell the participants this is something that's LM generated or human generated, people may have different, takes on whether this is something I should take seriously. I think this opens a very big, open space for future research, which we don't claim to be fully understood in this particular experiment.
Thank you so much. We have quite a number of questions. So should we just collect a first round and then, I mean, because we have limited time, so you get to decide how many of them we can take, if that's all right with you. I'll just read the first three and then we'll move on to another round. It's okay. All right. So, Emre Güzeldal is asking, do you believe the productivity gains are mainly driven by increased output within authors or changes in co-author network structure post-adoption also play a role here? The next question, I mean, this one I think was sent as a direct message. I can also share it with you if you cannot see it in your chat box, if you would like to take
Yeah,
notes.
maybe I can quickly respond to that. So that's a great
Okay.
question. Yeah, so we try looking into these things. So my impression is that we were not seeing that as a biggest driver of the results we were seeing there. I'm with you that in the longer term we should expect not just changes in numbers but changes in collaboration network, the labor force aspect of it, right? But at least until the mid of 2024, we are not seeing strong evidence in our data.
Mhm. Thank you very much. The next question is from Berke Elibol. This situation reminds me of the dead internet theory, where the internet is so oversaturated with AI-generated content that it feels non-human and sterile, beating its purpose. Do you think the academic production will suffer from the same problem as the proportion of AI-assisted papers increase? Also, do you think the situation hurt the validity of the metrics we use to assess researcher impact?
That's also a great question. So I would say in terms of metric, uh, overall, I would say not necessarily skirting the matrix, but I think at least it requires our seriously, revisiting these matrix that have been using. My 2 cents that some of the matrix may be more vulnerable than some others to this new wave of AIs. For example, if you just count the number of papers, that's no longer going to be something that's very telling. But whether some citation or normal citation matrix still be useful, at least to some extent, maybe. I don't have a very clear answer to that, but at least we need to revisit this very seriously. And also, it's a very great point about the dead internet theory. I've seen a lot of concerns over this. I will say I can see something that might happen similar to that, but not essentially in the exact way, right? So the idea of that internet is that people really want some of the social interactions or real human beings on internet information. And if you see all these bots talking about things, that's going to be very bad. I think for science, um, on the sociology of science aspect, you want to attribute individual scientific works to humans, to the incentive structure, etc. But from a scientific ecosystem aspect, I can also see some of the counter argument is like, what if AIs are indeed producing high quality scientific research? Right? What if they are doing better experiments? Then maybe we shouldn't be worried about that too much. I think we are now in this transition time where people have already massively using AI to produce research, while the specific quality of many of these research haven't been catching up with the best human scientific production. So that's where things get most concerning. Whether this will be a concern in the next 5 years or 10 years or so is something that we can bet. I can see optimistic people saying like maybe in the next 5 years, these AI written papers are indeed providing better scientific values, and maybe it's not a huge concern anymore. But we will see.
Thank you. Next question is from Ilayda Küçükapaca. I was wondering that in this current peer regulation period, what is the risk that hallucinations generated by LLMs and infiltrating the scientific literature could create a contaminated data set for future research? Do you think that in the future, a general suspicion of reliability grounding may arise against publications produced during this uncontrolled period? And could this create a perception of a dark age for this period in scientific history?
Wow, wow, I like this
We have a
comment.
lot of philosophical questions today.
I like this comment. So we are indeed having a separate project trying to quantify not every but some of the hallucinations in scientific production. So we are indeed seeing a spike in hallucinations. Not just the papers that didn't go through peer reviews, but something that we can say for sure this is giving you some misinformation. To what extent it spread, outside, it spreads within the scientific network is something that still requires a longer time to see. But I see your point is that if overall the perception is that science produced in this age may no longer be something as robust as produced by previous generations. There could be a structural shift in what kind of knowledge we build from, which could be concerning because we already know we are building on an increasingly older set of scientific papers. And if we are not trusting recent research, that's going to be even more concerning. I would say in practice, I would expect people not just, abandoning the entire generation of literature, but it could be the case that we are looking into other social signals when we deciding which papers we need to build on, right? One of my collaborators have this interesting argument is like it may be social signals. For example, if nowadays I will still build on 2025 papers. I won't just build on 1990 papers. But if I see some paper from someone I already know or from some researcher in our field that has been already been having a very good reputation, then more likely I'm going to trust that specific paper instead of a random paper I found on Archive or Google Scholar, right? But I do see this actually creating a lot of frictions, especially at the individual career level. For example, you can see some of the preprint servers have now been raising their bar for endorsement policy. Like if you are someone who haven't published a paper before, we are going to be very cautious examining your first paper because likely it's AI generated or AI assisted. So there could be social implications, I would say, not necessarily on the individual paper level, but on the individual career level, especially this new generation of, for example, ongoing PhD students. Basically, I think now assumption nowadays is like every one of them are using LMs, right? And to what extent we should trust this? In many cases, you actually bet on the PIs they are working with. Have they, received very rigorous training? I don't think this is a perfect solution, but unfortunately, this may be the heuristics that people will be using for quite a while.
Thank you. We have three more questions. Can we collect another round, or is that all right? It's absolutely up to you. Okay. All right, so I'm starting with the first one. Rumesa is asking, I wonder what you think about the underlying reason for the difference between the results of non-native English speakers and native ones.
That's a great question. So I don't think we have a 100% clear answer to that, but I do will say this is very consistent with the current discoveries that overall, in many cases, AI are more likely to narrow the gap rather than widen the gap between those who are very skilled at something versus those who are associated with relatively low skills. So if you think about, for example, scientific writing and reading as something that's at least weakly correlated with whether you are a native speaker or not, right? So if you are a native speaker, you may be associated with, on average, a higher efficiency of scientific writing, while if you are a non-native speaker, you may be associated with a lower efficiency or rate of scientific writing. So I'm thinking about AI as an equalizer. It could be the case that non-native speakers benefit more from LM tools, which is exactly what we see in the empirical data.
Thank you so much. The next question is from Helin Özdemir. LLMs are trained on the existing scientific literature, and scientists are now using them to write new papers, which in turn become training data for future LLMs. Over iterations, do you think this closed feedback loop could silently narrow the space of how scientific ideas are expressed and eventually how they're conceived? Essentially, could we end up in producing the same thinking patterns in science?
Great question. So there have been a couple of research around this point. For example, there has been a recent Nature paper by James Evans' group at U Chicago, where they explicitly look into something that's very similar to your question. Not exactly LMs, but they look at the overall, papers from I believe at least the 1970s until now. They look at papers using AI versus papers not using AI. In their case, it's not just AI for writing, it's more like AI for their data analysis and research. They did find that using AIs will lead to higher productivity, which is consistent with our analysis, but also a narrowing in scientific fields, which is if you look at those who are using AIs, they are more concentrated in the scientific topic landscape. So this is something that has been historically true. I will say, LLMs may, especially the new generation of these RAG-based systems, may open some new possibilities, right? So the assumption here is used to be a lot of machine learning tools are just connecting dots. It's just interpolating between human knowledge. But nowadays, we are seeing some of the foundation models have the capability of extrapolating beyond the frontier. So the stories could be different if you look into the near future. One thing that we have found, not really in the production side, but at least on the consumption side, suggests that LLMs may actually help you consume a more diverse set of references. So this is also documented in our December science paper, which I didn't have time to go through, but feel free to check out. Basically, you can look at what LM adopters are reading or citing after they have LM tools. This is not writing papers, but thinking about literature discovery or literature review. We are seeing evidence that LM adopters are more likely to read or cite papers that are books, which is something that I wouldn't read myself. It's just too much. We are also seeing evidence that LM adopters are more likely to engage younger references that just got published. They are more likely to engage with references that are associated with a lower citation So I think this suggests that overall, I think the concern is very valid, but we are also seeing possibilities where LLM compared with, for example, traditional search engines could lead to a more diverse set of scientific consumption. Whether that would lead to a more diverse set of scientific production is something that still need to wait for a couple of years before these papers really come out and enter our data set.
Thank you very much. And this is the last question, at least in my chat box. You show that, Sheval Çakıcı is asking, you show that revisions increase after feedback. Do you have any evidence that these revisions later improve acceptance or citation outcomes?
That's something we really wanted to see. I don't think we have an observational window that is long enough. So the thing here is we did this. We delivered the emails last year. So which means it already take a couple of months for authors to process that information and post the revision. If you look at, for example, citation outcomes, this is something that's going to take at least a couple of years to stabilize. So we are keeping an eye on it. The thing I can tell you is that I don't think we have a time window that is long enough, but hopefully we will see something in the future.
Okay. Thank you so very much. I mean, before we close the session, I'll give the floor back to you for any final words.
Not really. Thanks.
Thank
Thank you
you.
everyone for the attention. I really appreciate it.
We really had a fantastic kickoff for the semester, thanks to this really interesting thought-provoking presentation. And I'll pause recording now.